So where we finished on Friday was deriving a formula to compute diffraction patterns, though I didn't show you how we were going to use it. That's our main goal for today, is to take this formula, which I argued is basically a Fourier transform in 2 dimensions, and see how we can use it to get a function that will predict the diffraction pattern we'll see on a screen. Today for you, I'm going to do 2 examples that are both things you probably saw in lab, or at the very least you would have seen in lab this semester, if not, if we were still there. But I'm going to do calculate the pattern for a single slit aperture diffraction, and also the diffraction pattern for a double slit, which is, of course, something you've talked about on many, many occasions in many different contexts in physics. So as a reminder of where we left off, we're going to be making use of this formula in given contexts. So as a reminder of what these variables mean, we're going to assume the electric field hitting our aperture is a constant magnitude plane wave, which allows us to drop this E of xy from the integral. It becomes a constant, and if we only care about the basic shape of the diffraction pattern, we can kind of take this out and just drop it, since we're only really considering a proportionality. What that means then is that our diffraction pattern is going to be predicted by a Fourier transform of the function describing our aperture. You'll notice the Fourier transform gives us the electric field as a function of the components of the wave vector. However, the other thing we determined on Friday was that the wave vector can be written in terms of the distance from the aperture to the viewing screen, z, the coordinate along the viewing screen, that's x prime and y prime, and the wave number k. So k here just stands in for 2 pi divided by the wavelength of whatever wave we're talking about. So the strategy for solving these problems and computing the diffraction patterns is to compute this Fourier transform of the function t describing our aperture, and then convert the result, convert all wave vector components, kx, ky. So convert this from a function of kx and ky into a function of x prime, y prime, and z. And that will give us the wavelength in there. And so that will give us a function that we can then graph. So we can graph the electric field as a function of x prime and y prime on our screen. And the maximums of that function will tell us where the bright fringes are. The minimums of that function will tell us where the dark fringes are. So this is just a reminder of what the variables are. So x and y are, again, the variables on the aperture screen. X prime and y prime are the coordinates on the viewing screen. Z is the distance between the 2 screens. So z here in this problem is a constant, or something that we control at the very least. The variables we're integrating over for the Fourier transform are x and y. So we are integrating over these variables, which will give us a function of kx and ky, which, when we use these formulas to convert, will give us our electric field and thus our intensity as a function of the coordinates on the viewing screen. That's the general pattern. So integrate, convert variables to give us a function of the coordinates on the screen, and then we plot the function we get to get the diffraction pattern. So let's see how this works. We're going to do a 1-dimensional problem first as an idea, just to show you kind of how this goes. So this is only just a reminder of where these formulas come from. This angle in here in the x and y plane is given by x prime over z and y prime over z, which we can then relate to the x and y components of the wave number. But as long as you're willing to take these formulas here on face value from our lecture on Friday, this is less important. So here's where we're going to start. So we're going to start with a basic one-dimensional problem. We have an aperture that is really just a long slit, infinite in one direction, and a width d in the other direction. If we shine light through this screen and we look at shine light through this aperture and view it on a screen a distance z away. So here, this distance is z. We see experimentally a diffraction pattern that looks like this. We see one central big bright fringe, and then other smaller bright fringes in a repeating pattern, but the magnitude, most of the energy of the wave is kind of centered in this center big fringe here. If you guys have any questions along the way, please stop me. So what I want to show you is that by using this Fourier transform method, we can predict the function describing this pattern. So the first thing we need is a simple function that describes our aperture. And so that's t of xy, or in this case, it's one-dimensional problem, so it's just t of x. And basically, what we want is, we'll set the center of our aperture here. This is our origin, so this is x is equal to 0. So what we want is that for x coordinates that are in this region between positive d divided by 2 and negative d divided by 2, we want to let all the light through that hits that region. So what this means is our aperture function, or sometimes called our transmission function, in those regions it will have a value 1. Regions outside where the light is blocked, it has a value of 0. So when we take this result and plug it into our integral, effectively what it does is change the bounds from minus infinity to plus d over 2 and minus d over 2, because any values of x that are bigger than that, in those regions, the integrand is just going to be 0 anyway. So the effect of integrating this function, really, our Fourier, all that function does is change the bounds, and our Fourier transform becomes this integral, which is thankfully the integral of an exponential function. And we love integrating exponential functions because they're super easy. So we all know how to do this. So let me just kind of take this and plot the result for you. Or let me take this and like print out the result, plugging in the bounds. We have a minus 1 over ik that drops down in front, and I forgot a minus sign here. So just kind of fix that. And then we have the function itself. And we plug in the upper bound and the lower bound, which gives us, upper bound is plus d over 2, so that gives us a minus ikxd over 2. The lower bound gives us 2 minuses cancel out, and we get a plus ikxd over 2. And we could simplify, from here it's just kind of algebra, simplifying the function and then replacing kx with x prime. So we can use some algebra of complex numbers here to take this and rewrite this whole difference of complex exponents as a trig function. And I'll remind you guys that this is, I'm going to use, I'll leave it to you guys to show, but I'm using one of those identities that sine of theta is equal to e to the I theta minus e to the minus I theta divided by 2I. Hopefully you guys remember those. I'm using that to kind of take this and replace it with minus 2I sine kxd over 2. And doing some simplification. I's, of course, cancel. And we get our electric field as a function of the wave vector component kx. So the next step, now that we've solved the integral, we have the function of wave vector component. We want to replace the component in terms of the coordinate on the viewing screen. So this is where we go, and the next slide here, I'm going to take this number, or this formula that we found is going to be right at the top. So over here. And we're going to now use this relation. We're going to replace kx with this general relation that applies in the two-dimensional problem or the three-dimensional problem. Kx is going to be equal to the wave number 2 pi divided by lambda times x prime over z. Z being, again, the distance from the aperture to the viewing screen. So this gives us E as a function of x prime. And often it's more, you see the result written in terms of wavelength rather than wave number. So the formula I'm going to box here, or 2 really, I'm just going to replace k with 2 pi over lambda and cancel out other factors. If we want to get the graph of the intensity, then we get this function, which is essentially a function sine squared x over x. And if you go back to your calculus textbooks, you will see that sine squared x over x, or sorry, sine squared x over x squared, other constants aside, has this shape, a shape that more or less accurately predicts the diffraction pattern we see. A photo of such a diffraction pattern is showing down here. One exceptionally bright center fringe, then 2 dark fringes, and following that in a periodic pattern, smaller, bright, constructive fringes. And you can kind of see how the intensity drops off as we go from the center maximum to the first order bright fringes, and the second order bright fringes are visible but very dim compared to the center. This is a standard single slit aperture diffraction pattern. I have here the graph plotted in terms of pi x d over lambda z. But really, you could plot this versus x prime. We're really looking at the coordinate on the screen. Here, it's just the x-axis would be different. So this is kind of the first, all the other problems that you do with diffraction problems follow this pattern. Fourier transform, or I guess, find a function describing your aperture. Fourier transform to get E as a function of wave vector. Then replace your coordinates in terms of x prime, y prime, and then square to get your intensity pattern. Really, the actual, of course, the width of the pattern, the highest amplitude of the intensity is going to be proportional to the wavelength, z, where you are in the screen. And the actual frequency of the pattern, the space between the bright and dark fringes, will also depend on the wavelength and the size of your slit and how far away the screen is. But the general shape of the pattern, other than these things, really only depends on the coordinate, or here x prime, your distance from the center of the viewing screen. The other parameters there just change the properties of the graph, the frequency, the peak amplitude, but they don't change the overall shape or character of the function. You guys have probably seen this pattern before. I'm running through it to show you how this general method can calculate diffraction patterns. If there aren't any questions, I'll have another example for you. But before we move on, is there anyone confused about any of these steps in the problem? Okay, if not, then before we move on to our second example, let me introduce the first homework problem I'm going to have you guys do. It's based on this problem, but what I'm going to have you do is do the two-dimensional version of this problem. The integrals you get end up being very similar, so you can follow along with this example we just did. But basically what you guys are going to do for the first problem is to go through this process of Fourier transform and converting coordinates to get the diffraction pattern from a rectangular opening. That means with dx, let's say in the x direction, dy in the y direction. And basically you have to do the same problem, but with a two-dimensional integral. And I'm going to kind of show you what the answer should look like, both mathematically and graphically here. The diffraction pattern for a square aperture, this is a photograph here in the lower right for diffraction pattern using a red laser beam. But you get the same type of sine theta over theta pattern for the electric field, but the result is going to be, you will get this pattern in the x direction and the y direction. So what you should expect is something like sine x prime divided by x prime times sine y prime over y prime for this two-dimensional version of the diffraction pattern. Really what you get are two integrals very similar to what we did here on the last few slides that break up and you can solve separately. You should be able to follow along with the problem we just did to compute this. As for what this two-dimensional function looks like, you can see here, or three-dimensional plots of the diffracted electric field, or the intensity here. So again, it gives you kind of an idea of just how big the central maximum is compared to the first order and second order bright fringes. So that's going to be the first homework problem for diffraction. So I'll leave that to you guys later. I'm going to post these slides at the end of the class, so you'll have these slides ready for you in this afternoon if you want to get started on this. This one hopefully shouldn't take you too long as you follow the pattern on the slides. As for our second example, what I'd like to do now is do the double slit diffraction problem and try to use this method to predict the diffraction from a double slit experiment. So here, we're again going to treat this as a one-dimensional problem. Slits are really, really tall in the y direction, and the diffraction pattern is really only along the x prime direction. So what this means is that we need a transmission function for the x direction along the aperture. And what that would look like is something like this. Hopefully you can see this here and see how it makes sense. The light is only going to be able to transmit through the aperture in these regions here. So this region and this region. This is kind of like a drawing of a double slit aperture. Those regions, the transmission function will have a value of 1. So that's this region here. This is our first slit. This is our second slit. The slits have width W, and they're centered a distance A apart from the center of the screen, which we'll list as the origin. So there's this other parameter here of the distance of the two slits from the origin and the width. So I'm going to kind of do the integral here, and then the second homework problem you're going to get is filling in some of the algebra steps for this problem. So making the analogy from the last problem, this aperture function t is going to, again, really just change the bounds on our integral. Our integral is going to be 0 everywhere, with the exception of these two regions. There's one region on the negative part of the screen, and this one region on the positive part of the screen. So we have to just kind of we could write this single Fourier transform integral as two integrals with the correct bounds to integrate only over this area here and this area here. And that's what's shown here down below. You'll see the first integral is integrating over the negative part of tx, so this negative rectangle. The second integral here is integrating only over the positive region where Tx is not 0. And again, thankfully, these integrals we get, the calculus is very easy to do. Just an exponential integral. The bounds are a bit of a pain because we have two variables there, a and w, or two general quantities of which we don't know a number. But we can algebraically work this out. And I'm sure you guys know how to solve integrals like this once again. So let me jump ahead and just kind of color code this so we can keep track of things. So lower slit is, the lower slit or the negative slit in our aperture is green. The positive slit is in red. And doing these integrals, plugging in bounds, simplifying things, you get this. Sum of exponentials, and again, very similar to the last problem. And using a lot of algebra tricks with complex numbers and the identities from relating complex exponents to trig functions, you can rewrite this as a product of two trig functions, a sine times a cosine. And that's the part I'm going to leave you guys for homework to take from this line down here. I'm going to leave the last line, but clear off some room on the slide. And I'm going to have you show in the algebra that using those complex exponent and trig function identities, you can rewrite this function like so. And show that our electric field as a function of wave vector has this form. And we'll notice some properties here. Again, this is all just really algebra and playing around with some identities. But this part here is more or less the same thing we had in the first example. We have, and when we plug in for x prime, you'll see we're going to get a sine x prime over x prime again. So we have kind of our single slit aperture pattern appearing, with the exception of this new cosine term. So it's like we have the diffraction from the individual single slits. So you can imagine this first term as modeling or describing light diffracting through one of these slits and then causing a single slit diffraction pattern. That's this term here, we could call term 1. This other term describes how the light that's diffracting from the individual slits, from the both separate slits, interferes with each other. So that's term 2 here. So first term, the sign describes light coming from one slit interfering with itself. The second term describes the light coming from the two different slits interfering with each other. So, and you'll see this in a second once I graph this function for you. So here I'm going to go through now and make the substitutions that we made in the last problem. So kx becomes kx prime over z, and then we could plug in 2 pi over lambda for k, the wave number. So again, it's kind of a mess, but most of these things are constants of the experimental situation. The wavelength, the distance between the slits and the screen, and the width of the slits and the space between the slits. The only real variable here, the thing we want to plot against, is the distance along the viewing screen x prime. So let's plot this function, and I'll show you the effect that this new cosine term, due to this, the fact that there being two slits spaced this distance a, does. So what you'll see when you plot this function, and here are some, this is me plotting the square of all of that to get the intensity. So I'm using a wavelength of around 700 nanometers here. Well, really, you know, obviously, though this plot was made, I'm taking this plot from a different source. B here is the width of, let's see, B here is the width, B here is what I'm calling W. I believe, and D is what I am calling Z. But the end pattern kind of comparing to, we're plotting versus X prime. And what you can see is that now we have essentially these equally spaced, smaller, bright, and dark fringes. However, they're all modulated by the pattern we had before. So it's almost like we took our single slit fringe pattern and this cosine squared of x prime ends up breaking up that pattern into a series of smaller, smaller bright and dark fringes. So this is, if you did the double slit experiment in modern physics or in physics 112, and you looked at this in lab there, you almost certainly saw a pattern on the screen that looked like this. And usually the introductory physics way of calculating this problem ends up ignoring this whole single slit larger pattern. So the way of treating this problem in intro physics never really tells you why the fringes, you have these fringes that are equal size and equal space, but they drop off in intensity. And the intro physics way of analyzing this problem doesn't model that, and you can't predict that. And usually it's because the intro physics approach is ignoring the fact that you have single slit diffraction also from each of those individual slits in your double slit pattern. But treating the problem this way using the Fourier transform approach gives you a function that gets all of this, not only the equally spaced fringes, but how they change in intensity and these kind of smaller dark fringes, but then these larger, darker regions that correspond to the dark fringes in the single slit pattern. So this approach is a little bit more work, but it definitely gives us more predictive power, even in problems that we've analyzed or seen before. And it's interesting to see that if you take the limit of this result, if you assume that the width of the slits is much, much smaller than the space between them, you can get this, you can get the single slit diffraction pattern envelope, we'll say, to go away and just get equally bright and dark, equally spaced fringes from the double slit pattern, which is kind of fun. The easy and cool way to do that is to go back to the start of this problem, and instead of modeling the slits as an opening of width W, we'd have to model them as some kind of function that has zero width, but very high intensity right at its center point. And thankfully, I know for a fact all of you guys are in quantum mechanics and you studied functions like this now. And as you guys are probably guessing, the function you need to use here, if you want to model the problem with the space between the slits being much bigger than the width, T of x would really be a sum of two Dirac delta functions, one centered at minus a, one centered at plus a. And I know those things are annoying, but the great thing about them is that they make integrals very easy. So for your second homework problem, or I guess for your third problem for this set, you're going to compute that diffraction pattern for light passing through these very, very small, narrow double slits that are still a distance 2a apart. And the way to do that is to write T of x as these two delta functions and do the integral. And then that'll give you more, that third problem will give you a third example to practice. And what you should see is that all you really get if you use this delta function approach is only this cosine term. The sine term goes away. So you lose your single slit diffraction pattern, but you retain the stuff only from the double slit. And it should correspond to the results that for the double slit experiment that are in introductory physics texts. So that'll give you a third problem to practice this approach. Really, the main thing I want to do here with discussing diffraction is to really teach you how to use Fourier transforms to compute diffraction patterns. And I think these three problems for homework follow along from the two in the lecture, the two examples we did here. And hopefully this will make sense for you guys. I know this is like, it's kind of tough to do some like material this complicated online, but hopefully it's kind of clear on what the pattern and structure of the problems is. If you don't have any questions, then that's all I meant to cover for today. And on Friday, we'll discuss circular fringes because they have circular apertures making circular diffraction patterns because they have a whole separate type of complication, but they're very good. You kind of see them in applications in optics a lot. So if there aren't any questions, we're done for today, though I'm happy to hang out and discuss any of the details and the steps for these problems. Just let me know. All right, thank you all.